Hi, and welcome to this presentation. In this presentation, we'll take a look at failure mechanism effects and criticality analysis, and we'll give an advice to the province of Overijssel on the assessment of the structural condition of bridges. We are a consultancy firm named Simast, and our names are Simon Achterhuis, Marleen van Oerle, and Stan Bakker. The province of Overijssel thinks that its current method for assessing structural health of infrastructure is too simple. It allows for the interpretation and differences in assessment. They want to conduct a failure mechanism effects and criticality analysis instead. The failure mechanism effects and criticality analysis is a 7-step methodology. It identifies failure modes that make the asset underperform and determines criticality of elements through severity and occurrence. It ends with weights for the assessment of structural condition. The first step of the analysis is to determine the elements, and the province gave them to us. The first one is the abutment, the second the bearings, followed by joints, guardrail, pavement, and finally superstructure. The second step of the analysis is then to conduct the functional analysis. Here we determine element functions. They can either transform, transport, or store input attributes, and they can preserve condition or change condition. For the abutment example, its first function is to transform vertical loads from the bridge deck to the embankment. Its second function is to maintain and preserve horizontal and vertical stability, and its third function is to preserve the embankment and prevent erosion. However, we know that assets are complex systems, and therefore elements have more than one function, and functions are fulfilled by multiple elements. Therefore, it makes more sense to us to define overlapping functions, which are shown here. They are transform loads, preserve component connections, preserve superstructure integrity, preserve user safety, and preserve user comfort. We can then move on to the third step, which is defining the failure modes for which these functions underperform. We used 7 failure modes, and for the pavement, these include wear and tear, component corrosion, stability and soil erosion, collisions, overload, and biohazard. The 7th failure mode is fatigue, but it does not apply to the pavement, so it doesn't have an example. However, we used all 7 failure modes to assess all elements. The fourth step is then to establish the effects or the severity of these failure modes. How bad are the cascading effects, which we determined by using a 4-point scale ranging from minor to catastrophic. This table shows the severity for the abutment, and what you can see is that overload has very severe effects, while biohazard doesn't. The 5th step is then to establish the occurrence of these failure modes based on the causes. We used a 6-point scale ranging from incredible to frequent. What we can see then, if we look at the abutment, is that stability and soil erosion, for instance, is very probable, while failure modes such as wear and tear and collision are almost incredible. The 6th step is then to calculate criticality, which is done by multiplying occurrence with severity. The criticality scores are given in the table, and important findings are that the pavement is critical because of its high occurrence and severity of the failure for user-oriented functions. The superstructure is also critical due to its major transforming functions. It's subject to frequent failure modes. The abutment is less critical because it has lower occurrence failure modes, and the guardrail is also not critical because its failure modes are of lower severity. The 7th step is weights and priority. Here we normalize the criticality scores into weights. This is the prioritization we think should be used during the assessment of structural conditions of bridges. This ranking is pavement, superstructure, followed by joints, bearings, abutment, and finally guardrail. This is our advice, and it should help the province of Overijssel to better understand infrastructure health based on critical elements. We are Simast, and thank you for watching.